And we're back. Welcome back and happy Tuesday. Today we will finish up our module on radial basis functions. But before we begin, the reading is supplementary chapter number 6. It's on the course resources section of the Blackboard, section 6.3 on radial basis functions. Homework number 3 is due Thursday, the 22nd, that's Thursday, at the usual 11:59 and 59 seconds p.m. Why don't we continue? So when we last met, we talked about a radial basis function classifier, and in this, similar to what we did with PLA, we used linear regression, exact interpolation as it's called for radial basis function, and we took that solution and input it into our sine function, our nonlinear function, to make it a classifier. And it's exactly what we do also in the radial basis function case. So let's take a look at comparisons between radial basis functions and other techniques. Now, there are a class of similarity-based methods that take the label associated with data points and effectively propagate it to new inputs. And it's done by looking at what is nearest in feature space, this idea of birds of a feather flock together. And so the idea behind that is that when data points are similar in their location in feature space, that means their feature values are very close to one another, and things that have similar or same feature values are the same object or class or thing. And so what these k-nearest neighbor types of approaches do is that when you have a data point, you adopt the y value of the nearest point. Now, of course, you might ask, which one? Well, you don't just take a single nearest point. For smoothing's sake, you take the k nearest points within the training set using things like, for example, Euclidean distance, but it's not limited to Euclidean distance. And so when you increase k, what happens? Well, this makes the change in feature space associated with various labels, it makes it much smoother as you go from one point to the next. Now, instead of using k-nearest neighbor, one of the things that you can use is the radial basis function, and that also has the effect of smoothing out the decision boundaries of something like a k-nearest neighbor or similarity-based method. And so when you're doing k-nearest neighbor, it's effectively using a basis function, but it's not the Gaussian radial basis function. It's a cylindrical basis function that looks like the following. And so this is certainly radial. You can imagine your in-sample point over which this cylindrical basis function is centered. That in-sample point would be right here, xn, in the center. And then radially outward, it's the same distance where this influence is defined. And then once you get to that distance, it drops off to 0. And if you were to use this other basis function, the result that you get, the effect to do a nearest neighbor type classification scheme, you would get the same effect as k-nearest neighbor. And so if you center this cylindrical basis function over each data point, well, imagine this diagram on the left, where feature space, we have our first feature, x1 hat, along the horizontal axis. We have our second feature, let's call that x2 hat, along the vertical axis. Now, of course, in the cylindrical sense, if you center that basis function over each data point, you're going to get a circular region in feature space that's going to be associated with the label, ground truth label, for each data point. And so while it certainly, with the cylindrical basis function, it won't look like the following tessellation, this tessellation on the left is what you get from k-nearest neighbor. Now, it'll look more uniform in terms of being cylindrical shape, and based on the length of this influence, those circular regions are going to be larger. And so here we have our tessellation, and this similarity-based method doing k-nearest neighbor is precisely a radial basis type approach, or rather a basis type approach, where you're using a different basis function, the cylindrical function, versus the k-nearest neighbor approach, cylindrical basis. And so when you have a similarity-based method, one of the goals then is to make the change less abrupt. And as you can see here with k-nearest neighbor on the left, we start out where positive, and then it transitions to negative, and then transitions to positive. And you can have a lot of flips from positive to negative associated with regions in feature space. Now, of course, you can get this smoothing with radial basis instead of using something hard in its influence, such as this cylindrical basis function, which is more similar to doing k-nearest neighbor. And so let's take a look at radial basis function with another type of similarity-based method with clustering. Now, of course, with clustering, you're using the feature values, i.e. the location of data points in feature space, and their distance from one another in order to judge how similar to one another they are. And so in this, we have some number of data points, n of them, and we also have big N, many in-sample points. Now, of course, that introduces a very large number of parameters W because N is the size of your data set. Now, we could absolutely do radial basis function for clustering-based similarity method, but in order to reduce this complexity, we want to get away from having N many parameters, W1 through Wn. So instead of using each data point, associating that with a weight vector, we're going to designate a smaller number, k, big K, of so-called centers. And these centers are then going to be representative of the data points, and we're going to use that to drive our clustering. So let's define a set K, or number K, that's going to represent the number of centers, and K, by definition, is much less than the number of your in-sample points, N, the size of your data set. So we're going to use as the center of the radial basis functions, we're going to use our centers, mu1 through mu k, instead of the individual big N many in-sample points. Now, these mu's are all vector valued in d dimensions. And so we have each one of our data points, xi, in R super D, d-dimensional real valued space. And likewise, we have each one of our centers, mu I, also in d-dimensional real valued space. So how do we compute one of these centers mu? Well, we start out by randomly selecting them. But you can think of one of these mu effectively as being the sample mean associated with each one of the features in, or those dimensions in d-dimensional real valued space. And so now our radial basis function, in using these k centers, mu1 through mu k, instead of our n many in-sample points as the center of the radial basis function, we get the following definition of our working hypothesis. We say h of x is the sum. Now you're summing over the number of centers of our weight wk, and then we have our radial basis function modulated by gamma, and then we have x minus each one of the centers. So it's the radial distance with respect to each center instead of with respect to each in-sample point. So this then changes the learning problem for radial basis function clustering purposes. How you choose the centers are mu's, and then also how you choose the weights. And so essentially, we want to take each one of our in-sample points, and now we're going to minimize the distance between each one of our in-sample points and our k-many centers. And this is going to be our k-means clustering. So we're associating our data points with the closest center, minimizing along the way as we go along. And so we're going to first begin by taking our in-sample data, and we're going to split it into a set of clusters, and we define each cluster as S1 through S big K, where each of the S's is going to represent some subset of our entire data set. Now, of course, how do you make this assignment? Well, we'll get into that when we talk about Lloyd's algorithm for actually doing the clustering. But at this juncture, what we essentially, if we want to minimize the distance between each data point xn and the closest center, we effectively take each center, all of those data points within the center, a particular center, the kth one. We're going to take the distance, the square of the magnitude, and we're going to add them up. So this is within or you could also say about the kth center. So essentially, we add up the distances between each data point within a cluster and the center for that cluster, and then we add that across all the clusters. And we do that for the first cluster, the second cluster, third cluster, up to and including the kth cluster. This is so-called unsupervised learning. In this, you'll notice we're not touching the ground truth label. All we're manipulating here is evaluating or examining the value of the features, not the labels. So this is unsupervised learning, but the problem is this is an NP-hard problem. Why is this an NP-hard problem? Well, if we have each one of our in-sample points, x1 through x big N, and we wanted to find the assignment of points to clusters associated with the minimization of this expression, the cluster criteria you could call it, we're going to explore all of the assignments of these points to clusters. So then if you want to associate x1 with a cluster, you're going to have k many choices assigned to cluster 1 through cluster k. And then for x2, you're also going to have k many choices assigned to cluster 1 through cluster k. And that means you're going to have k many choices for x1 times k many choices for x2, up to and including k many choices for x big N. So that's going to result in k to big N power different assignments that you'd have to search through for this particular minimum. And that's the best cluster assignment. Now, of course, because it's exponential in the input data set size, you can't solve this exactly because it's NP-hard. And so you need an approximation in order to do so. And said approximation is called Lloyd's algorithm. Lloyd's algorithm solves the clustering problem, but it does it iteratively by holding one parameter fixed, solving for the other, and then holding the other parameter fixed, solving for the first one. And so essentially what you do in Lloyd's algorithm, you start out with an initialization of data points to cluster. You just randomly assign them to cluster once, and then you update the center. So that's your mu sub k value. You update the center by going through each cluster once it's assigned, points assigned to each cluster, and you compute the center, the mean. You sum together all of the feature values for all the points in each of the clusters, and then you multiply by 1 upon the size of the cluster, the cardinality of each that cluster. And so once you do that, then you hold all of the mu k's fixed, and then you reassign the points based on a criteria of which point is closer to which center. So when you assign the points to centers, because of this idea of closest to that we use as a criteria for the reassignment, the distances are going to get smaller. These distances for this inner summation, they're going to get smaller because you're reassociating these points to clusters based on this closest criteria to the cluster center, representing the cluster. And so once you do the reassignment, you then go back to the first step and you recompute your new value for the center. Now, because the points are now closest to or in the cluster associated with the closest center, when you recompute the center is going to change. And then after that, you fix the centers and then go back to the reassignment. And you keep iterating over that some number of times until convergence. You reach a local minimum. Now, of course, this is just a local minima and not the global minima because you're not searching all k to the n many assignments of points to clusters. If you could exhaustively search that, evaluate this, and choose the assignment that where the minimum occurs, that would be guaranteed to give you the global minimum. But it's exponential in the input size, and it will never converge. All right. So that's Lloyd's algorithm, and what this gives you, it gives you the assignment, Sk, of points to clusters and the associated centers, which are the representatives of those points in those clusters. And now you can use these representatives, these mu sub k's, as the centers associated with the radial bases. Okay. And so you can make a comparison between support vectors and radial basis function centers. And these centers in radial basis function, as we said, are representative of the data points that are closest to them in that cluster, represented by the center. If we take a look at this graph on the right, we see this center is representative of those points in feature space. This one representative of those points. This is representative of those. This one representative of those. This one representative of those. This one's those. This one's representative here. Representative here. We have representative of here. Now, of course, if you look at these clusters, they involve, in many cases, points that are positive examples as well as points that are negative examples. Another observation is that these cluster centers, they're all in black. That means they don't really have labels. That's not what they represent. In fact, they don't even consider labels. All they're comparing is the feature values or the position in feature space that each data point occupies. If we cast our attention to the support vector machine, well, support vector machines, you pay attention to the label. And when we look at the support vectors, in this case, we have 9 support vectors, and we also have 9 centers on the right. But if we cast our attention to this graph on the left-hand side, we have our 9 support vectors, and you'll notice that these support vectors, they hold up the decision boundary, and they define the hyperplane. As we said, the weighted sum, these alphas that are non-zero, the weighted sum of the alphas times the support vectors will give you the hyperplane. And so here we see our 9 support vectors. They are labeled, and this green curve, that is our ground truth target function. And while the two are not different, it's important to compare and contrast them. Support vectors use the class labels to find data that's representative of the hyperplane. And for radial basis function clusters, it finds points, the centers. They're also representative, but they're representative of the inputs based on their feature values. And so we can draw a comparison between our Lloyds algorithm and support vectors. While they're not the same, they have different properties associated with what it is they represent. All right. So let's then take our version of Lloyd's algorithm that uses K cluster centers, and we can actually compute what the weight vector W is. And so here, when we solve the equation of that sum over all of the centers of our weight vector positions W, our weights, times the radial basis function of each input n relative to the center with its corresponding label yn, we're trying to find this equivalence here. And so if we do this, well, we have n equations because we have n in-sample points, big N, many in-sample points, xn, and its corresponding yn, and that's going to correspond to each one of the rows here. So that's going to be big N rows. That's the n equations. And then we have k unknowns, because the other unknowns are these w's, and there's one w for each one of these cluster centers mu. And so if we look at this, we have k, and that's going to be our set of unknowns. So we have now n equations in k unknowns, where k, the column measurement, is going to be much smaller than n, the row measurement. And so certainly we can solve this because this is a rectangular matrix. We can't just take the inverse like we had similar when we had the exact interpolation case, but we can use the pseudo-inverse to solve for W, our unknowns. And so the pseudo-inverse is listed here, and we can call this a phi matrix, just like we had before with the exact interpolation case. And we get pseudo-inverse, assuming that phi transpose phi is invertible, where W is phi transpose phi inverse times phi transpose times a target vector y, where y is a real value. Okay, and so we can use this to determine our big K many weights W in order to solve this Lloyd's clustering equivalent. So let's relate radial basis function to neural networks. And so with our radial basis function, thinking of it as a network, when we examine the radial basis function, well, let's assume that all of our centers are fixed. They're values, they're constants. So we have, for our input, we have x minus mu. So that's relative to each center, to each radial basis center on our mu's, our cluster centers. This looks like a feature. It's a nonlinear transformation, and this nonlinear transformation depends on the data set. And so this is no longer a linear model. So we take our input, we then feed it through our radial distance, and then we input that through a nonlinear function. That's our feature. So at this level, our first hidden layer, that's a feature. We're extracting a feature that's dependent on the data set from our data. Now, we take a weighted combination, this is where our W vectors are, of those features. And so the value of the features depends on the data set, and it also depends on these mu's, our cluster center. But nonetheless, when we relate this radial basis function to a neural network, we can actually cast what it's doing when we find our W vectors by the pseudo-inverse using these K centers. We compute this pseudo-inverse. That's like finding our weight vectors, but we're doing it in closed form in one fell swoop mathematically. And it's exactly like training a neural network, only using the pseudo-inverse. Now, if we compare that to a regular neural network, well, with our neural network, we have our weighted sum of our inputs, input that through a nonlinear function, our hidden layer, and through backpropagation, we learn the weights. And so these particular features, there's some features, they're learned. They're learned via backpropagation. Why do we say they're learned? Because you're trying to find the combination of these nonlinear functions over the data that most closely mimics, through your working hypothesis output, closely mimics the label by the unknown target function. Now, this radial basis function network is like a support vector machine. You can think of this first layer, the features we alluded to before, as selecting a kernel, a radial basis kernel to be precise. And the second layer then takes that linear combination of our radial basis kernels. That's the linear part. If the distance is very large, the contribution from that particular feature is going to be small. And so in this case, this radial basis function network acts like an SVM, but it only counts local contributions relative to certain regions of feature space defined by the cluster center, the mu's, mu1 through mu big K. But these features are learned through backpropagation. It's exploring and saying which feature should we take. Here in the radial basis function network on the left, it's saying, okay, which influence should be counted and which should not be counted. And so they're very much related to one another. And if you look at the early work in support vector machines, you'll find that support vector machine was done in the earliest incarnations in a support vector network as a neural network. All right. And so now, how do we learn this gamma? This gamma can also be learned as a parameter. And with our radial basis function network approach, we have our working hypothesis defined by our big K many parameters W, but we also have this gamma. Let's assume that our mu's were already fixed. We ran Lloyd's algorithm, we got our mu's, and now we want to find what our gamma is. So what do? Iterative approach, which is very much like expectation maximization, which is used to solve a mixture of Gaussians. And so if we think of our W vectors, those are mixture weights, and our exponential, that's like a form of Gaussian. Well, it is a Gaussian, a very simple Gaussian. And so with this iterative approach, again, we're going to alternate. We're going to fix our gamma, and using that, solve for W. Now, that solution for W, it could be through a pseudo-inverse. And then, once you find those W's, you fix your W's, and then you minimize error with respect to your gamma. And so you can do that different ways, as through gradient descent, and then you get a different set of gammas, and then you set them, and then you go back and choose your centers as you usually do, keep them fixed, and then you go back to fixing gamma and solving for your W's. And then you keep doing that until your gamma settles down. And now, of course, with this, you don't have to have the same gamma for each one of your centers. You can have a different gamma, and in doing so, you're saying, okay, well, count this particular set of points over this center, So what does this radial basis function give you? Well, let's compare it to a support vector machine solution. Now here in the green curve, we have our ground truth target function. And when you solve the support vector formulation using a radial basis kernel, you get a solution that looks like the following. You get a set of alphas, and these alphas that are non-zero are associated with the in-sample points xn that are the support vectors. And so we take our W transpose x plus b and take the sign of that, and of course our evaluation of W transpose is alpha n yn times the kernel evaluation, which has the inner product between x and each one of our in-sample points that are support vectors. And so with this kernel evaluation, we take that and we only sum those particular kernel evaluations associated with the support vectors. With the radial basis function implementation for classification, we solve our radial basis function approximation, our hypothesis, using k-centers, and we solve this score, our sum for each one of the k many centers of the mixture weight W times our radial basis function evaluation relative to the centers. And of course, we solve for our W's through pseudo-inverse, and then we alternate to get our gammas, keeping our centers fixed as a result of first round of this Lloyds algorithm. And once we do that, we take our final best hypothesis and we input that into the sign function. And so in essence, the centers, our mu's, in the radial basis function classification implementation serve the similar role, not the same, but similar role as support vectors. And the role that they serve is this representative of your data set. In the case of support vector machine, these xn, the support vectors, they're representatives of your decision boundary. And so essentially, they're similar to one another. And you can solve with support vectors. You, of course, solve the max margin classifier with a kernel, radial basis kernel, and use quadratic programming. Now, with radial basis approach to classification using these k centers, you're using Lloyd's algorithm to get your cluster assignments and therefore your centers, and then pseudo-inverse and maximize them. All right. So this is a comparison between radial basis function and support vector machine. So let's take a look lastly at the relationship between radial basis functions and regularization. Now, you can actually derive radial basis functions purely based on a regularization argument. And so let's say you have a one-dimensional function and you want to make a smooth approximation. So what do? Well, you have your squared error loss between the real value target value, yn, and your output from your working hypothesis. So given that squared error loss, that would be your expression for in-sample error. We're summing across all of the 1 over n in-sample points. So you would add to that a smoothness criterion. How do you define your smoothness? This smoothness can be taken as a penalty term where you include a multiplier that tells your optimization how much to pay attention to the smoothness. And so what do you do for the smoothness? Well, you take the integral of the second derivative or kth derivative more generally over the support for your function. And when you take this derivative, you then add up for each one of your coefficients, you combine set of derivatives. And so with this, if you were actually to solve this, this term looks like a Taylor series approximation for e to the x for an exponential form. And so this gives you exactly the radial basis function. And the best interpolation is also the Gaussian. So some term looks like a Taylor series for the exponential. And so radial basis function does come from regularization, both in spirit as well in derivation. And it is also no secret that the Gaussian gives you the smoothest type of interpolation. So with that, that's all I had. Radial basis function is immensely useful. You can use it for regression through exact interpolation. You can use it for classification. application. You can use it for a whole host of things, clustering, and it's just a very useful function or an approach to similarity-based methods. On top of the fact that it makes a great support vector machine kernel, it has infinite VC dimension. So with that, we'll end there. That's all I had. And as usual, please stay healthy, stay safe, and I'll see you all